Hello everyone. In this video, we will continue to examine topic D.3 cosmology, focusing in on the accelerating universe and redshift. So, the third major discovery, we've examined two, Hubble's law and the cosmic microwave background, that we'll focus on, has been made, as these things go, very, very recently. And in fact, the central discoveries to what we're about to discuss happened in the late 90s. And that is the acceleration of the expansion of the universe. So, question, what happens to the expansion of the universe over time? When we estimated the age of the universe using Hubble's constant, we did so by assuming that the universe expanded at a constant rate over time. As it turns out, we have good reason to believe that the expansion of the universe is not slowing down, but is in fact accelerating. For a long time, we had a single answer to this question, which is that it should slow. The expansion of the universe should slow down. More or less, it can get more complicated than this, but more or less, gravity pulls matter together, or gravity curves space-time inwards. The idea is over time, no matter how fast galaxies are moving apart, eventually galaxies may not be pulled together completely, but they should at least be slowing down because there is that long-range force. It is the only one of the four fundamental forces that acts at tremendous distances, and therefore the only one that should matter at cosmological scales. As a result, no matter whether gravity sort of eventually pulls everything back together, the expansion of the universe should be slowing down. This was the answer for years and years and years. And it's an astounding fact that we have good reason to believe that that is not the case. So, in particular, Saul Perlmutter, Adam Rees, and Schmidt, whose first name I cannot remember at the moment, measured the rate of expansion using Type 1a supernova at high redshift to determine R, the scale factor over time. This is combining a whole bunch of information we've discussed, but I want to go over it in detail. So Type 1a supernova, remember those are our highest cosmic distance ladder probes. Type 1a supernova are the tools we use to measure the distance to the very farthest away things. We're using them to sort of constrain the scale factor R over time. Because that redshift is related to the scale factor, then by using the Type 1a supernova, we get both a distance measurement and a measurement of the scale factor as it was then. Another way of thinking about that is as you look farther and farther away, you are also looking farther and farther into the past. And so it gives you a way of examining how the scale factor has changed over time. We'll come back to this chart a little bit later, but this sort of shows how different theories for how the expansion of the universe has gone might be plotted here. So the scale factor R is shown here. That's 1 right now. Although perhaps it's not obvious, the slope of that line being constant is sort of related to the current value of Hubble's constant. And then as you use Type 1a supernova to look further back, you can discover sort of the shape of that change over time. If you have a gravity-dominated situation, if gravity is slowing everything down, you would expect that scale factor to at least bend downwards. Those of you who have calculus, you'd expect that second derivative to be negative. But in fact, we find that that second derivative is positive, and we're going to look at the evidence for that in a bit. So we use this equation, the redshift equals R over R naught minus 1. R naught in this case is the scale factor in the past, and R right at this very moment is equal to 1. Therefore, if we want r as a function of time, which gives us the scale factor in the past, we can relate r as a function of time to that redshift. We rearrange the equation, and so simply by measuring redshifts of very far away things, we can measure that scale factor. That's the key ingredient. All right, so what happens? Well, the expansion is accelerating, and the evidence can sort of be summarized in this particular diagram, which is combining multiple teams' work. So both the SCP, the Supernova Cosmology Project, which is a project I worked on for a little while, and the High Z Supernova Search. And in both of these cases, the dominant evidence from Type 1a supernova is that they are all slightly dimmer, well, slightly is the wrong word, significantly dimmer to within our measurements than expected. This suggests that they are farther away, and therefore, historically speaking, that the expansion is accelerating. They are farther away than they should be, given an expansion that has been slowing down or would have been slowing down. And that can be seen here. So this plot shows the redshift z, which as we showed is directly related to the linear scale of the universe. Notice that with higher redshift, so these are high redshift galaxies right here, high redshift galaxies, they are telling us things about the scale factor further ago, so longer ago. If the linear scale of the universe relative to today is 0.5 at this particular point, that means the universe was half the size. Everything was exactly twice as close together at this point. And so what's plotted here is, on the vertical axis, is how bright those supernova are. And we discover that they are, in general, dimmer than you would expect. Now, this is sort of a diagram to be sort of with vacuum energy and without, but we'll come back to that later. That just means that if the supernova are above this line, you expect them to be supporting the idea that the expansion of the universe is accelerating, and if they are below this line, they are supporting the idea that the expansion of the universe is decelerating. And although the data has been supplemented since, this was the smoking gun. This was the single piece of evidence combining the different sources of very high Z supernova detections that led us to believe that the expansion of the universe is accelerating.